Good morning. Can you hear me?
Good morning, I can hear you.
Yeah, okay. So we have today meeting of the Joint Commission of Environmental Technology. And there is one point in this agenda today. It's PhD defense of Kalev Uiga on modeling and experimental measurement of the closed equilibrium systems of calcium sulfate H2O and then strontium sulfate S2O, H2O. And in the beginning, I would like to introduce our commission. I am Guramander, head of the commission, professor of physical geography and landscape ecology. This is the joint commission over different institutes, ecology and earth sciences, chemistry and physics. So it's really very multidisciplinary commission, and the members of the commission are, first of all, our distinguished opponent from the Vilnius Gediminas Institute of Technology, Professor Marina Valentukevičienė. I hope my translation was more or less perfect. And the commission members are Dr. I read here to be correct, Sirveli, Dr. Barjan Tam from Tallinn Technical University, Professor Kalev Uiga from the Institute of Ecology and Earth Sciences, Dr. Paavo Tenno from the Institute of Chemistry, and Dr. Jan Pisek from Tartu Observatory, which is also part of this commission. And also we have here Professor Markus Vettemaa from also ecology and earth sciences, and Dr. Uno Kazak from the same institute. So we are more than complete. Minimum 6 members of the commission are needed to provide this process. First of all, before I give the word for the candidate, a very short reading of your curriculum vitae. Kalev Uiga was always related to Tartu University, beginning on environmental technology studies at bachelor level or the master level, and now it's finalizing his PhD level. He has published several papers in co-authorship. 3 of them are in first authorship, and these 3 papers are also included in the thesis. Oh, actually, there are 6, all of them. Well, now the word is for the candidate to present briefly during maximum 30 minutes your main outcomes of the studies. Please.
Yeah, thank you.
And then we can continue with the discussion with opponents. Yeah,
okay. Ladies and gentlemen, esteemed members of the Council of the Academic Board of the Environmental Technology in University of Tartu, the thesis committee component, colleagues, and the guests, I will defend today my PhD thesis with the title Modeling and Experimental Measurement of the Closed Equilibrium Systems of Calcium Sulfate H2O and Strontium Sulfate H2O. And the importance of current thesis is also related to the investigation of hazardous waste generated by oil shale industry in Estonia. For example, the interaction of semi-coke residue with water generates highly alkaline sulfur-rich leachate hazardous waste for the environment, which requires further processing or treatment. Besides, part of sulfur from it is emitted into the atmosphere when an ecologically toxic gaseous hydrogen sulfide forms in an anaerobic conditions. And first, I give overview of our, okay, next slide. The aims of the study are in contents where I give overview what were the aims of current study. Then there comes the introduction part, then materials and methods which were used, and after that results and discussion, and in the end conclusion comes. And first I would like to about the aims of the current PhD. The aims were the following. First, to investigate the dissolution process of calcium sulfide and strontium sulfide in water by using potentiometry. The second goal was to upgrade mathematical models for the calcium sulfide water and strontium sulfide water closed equilibrium systems based on the proton transfer principles and to validate them experimentally. And the third goal was to determine the size dependence and average concentration of formed particles in the systems by using nanoparticle tracking analysis technique. And the last goal was to calculate the value of the solubility product for nanoscale particles in different equilibrium systems. And to do that, here it is the current theoretical models are mostly based on the novel, are thermodynamically, but our novel proton transfer model is more precise than the thermodynamically calculated ones are. And although calcium sulfide and strontium sulfide are only slightly soluble in water, their reaction with it causes a significant increase in the system's pH value. And the determination of the exact concentration of formed sulfur species is still complicated, and the known values of the second dissociation constant of dihydrogen sulfide in the literature were compared with the experimentally obtained results in case of solid calcium sulfide or strontium sulfide. And the closest correlation between the calculated and the measured values of parameters of the investigated systems was at KH2 value 1.202 in power -15 given by Knox. And here are the table of known values of solubilities or calculated solubility product values of most common alkaline earth metal sulfides and hydroxides. And as shown, the lowest solubility is in case of magnesium and its compounds, because its ionic radius is the smallest and it hardly dissolves in water. So it's the lower solubility is caused mostly for this reason. And other sulfur, like calcium sulfide, strontium sulfide, and barium are more or slightly soluble. And the best solubility is in case of barium, where it may be nearly 80 grams per liter, according to literature data. And, in this table are shown known values of negative logarithmic of a second acid dissociation constant of the hydrogen sulfide and use determination techniques given in the literature at room temperature. And as shown from this table, there are also a big difference and nearly 7 orders of magnitude from 12 to 19 is this values different to each other from each other. And we used pH measurement technique, and it's generally remains into pH scale, but other methods give a remarkable higher result. And it also depends on the determination method what we use. And here are shown the structural scheme of distribution of ions and molecules in the closed equilibrium systems of calcium sulfide water and strontium sulfide water. And that when we dissolve strontium sulfide or calcium sulfide, then solid sulfide reacts, forms two ions, sulfide ion and the metal ion. And the sulfide ion reacts further with water and binds protons from it and forms hydrogen sulfide. And when we add more salt, then the hydrogen sulfide forms in the system. And when the system is opened, then the dihydrogen sulfide goes out of this system to the gas phase. But we, in our case, we viewed only the water phase, and we omitted the gas phase. Was because the volume of gas phase was very little, negligible. And when we add more salt and we exceed the solubility product concentration of calcium hydroxide or strontium hydroxide, and then the latter precipitates out from the system, and the pH remains unchanged at the last step. And here are shown the these test systems what was used with the strontium sulfide or calcium sulfide aqueous solution. And here are shown that we used inert gas in order to avoid oxidation and purged out oxygen from water, because oxygen reacts quickly with sulfide ions, and we don't get the right results if we doesn't remove oxygen from the system. Then we have to about half hour to purge it out from in the case of this system. And the liquid phase volume is higher than the gas phase as shown in this photo. And we used the pH meter to register the results, and the sampling was done quickly as soon as possible after the equilibrium was established in the system, because in order to avoid oxidation. And here in this photo you can see the measurement of gas phase where we used alkaline solution, in our case sodium hydroxide, to bind dihydrogen sulfide from this gas phase. Here is the water phase, but it also depended on the duration of experiment, how much dihydrogen sulfide was bounded by 0.5 molar sodium hydroxide solution. And then we calculated the average binding rate of this dihydrogen sulfide, and we got the result. The average result was 0.827 in this gas phase experiment. And here are shown the correlation between the theoretical, what was known, KH2 value, what was taken from Knox, and our results. And as you can see that the results are quite similar, and at some point there may only be maybe the measurement accuracy or determination problems what may cause that this is not exactly as theoretically shown values. And in x-axis are shown logarithmic concentration of strontium ions, and in y-axis are shown the corresponding pH values. And as you can see that even at small concentrations, the pH value rises very quickly. And it also are shown here in this table. In case of calcium sulfide, when we add it into purified water, then the measured concentrations, even at small amounts, about 0.303, the pH corresponding level rise to 10.6. And if we added more salt, then we exceeded the solubility product of calcium sulfide, and the precipitate occurred visually in this solution around 1.6 millimoles solution concentration. And here are shown the pH profiles and the duration of experiment. And there are also shown that the pH increase was very fast. And even at small concentrations, it reacted with water and raised the pH over 11 if we added more salt. And then at last step, when this profile was and the equilibrium was established, then we registered the final pH value, and also took the samples as soon as possible. And here in this graph are shown the calculated and measured EDTA titration values of strontium ions in the aqueous solution in the range of added salt concentration between 15 to 10,000 milligrams per liter. And here you can also see that when we add a small amount of salt, then it's almost the same as theoretically calculated one's values. But when we add more salt in the system, then some salt remained undissolved and remained as a precipitate, which was visually shown in solution. And at the last step, at this point, then even if we add more salt, the pH didn't change at all, because the solubility product of strontium hydroxide was exceeded. And here are seen the same in pH scale. Here are shown the concentration on strontium sulfide in millimolar concentration in this graph, x-axis, and here are seen in y-axis the pH corresponding to this added salt amount. And here you can also see that when we exceeded the solubility product of strontium hydroxide, then the pH value remained around 13.2 value, and it didn't change anymore. And here in this graph are shown the correlation between the experimentally measured hydrogen sulfide, it was measured spectrophotometrically, and the hydroxide ion, which was measured by pH meter potentiometrically at the pH values, at the same pH values. What was measured was 15 to 10,540 milligrams per liter. And as you can see, that the first step, when we add more small amounts of salt, then this hydrogen and hydrosulfide ion concentration is almost the same. But when we added more salt, then the difference between hydroxide ion concentration and sulfide ion concentration rises. And because some salt remains undissolved, then it causes that this is a little bit lower than theoretically can be calculated. And here are shown the results of the nanotracking analysis system measurement. The comprehensive size of the formed particles in the closed systems of measured ions are shown. And when we added a smaller amount of salt, then it dissolved completely into, and there was no particle shown. But when we added more salt over 0.1 millimolar concentration strontium, in case of strontium sulfide or calcium sulfide, then the first nanoparticles appeared at the size over 10 nanometers, and these particles can be detected by nanosite system, and then we can registered also. And when we added more salt to the system, then the smaller particles coagulated and formed the bigger particles and disordered aggregates. And when we added even more, then the last step, solid crystals forms into system and the crystalline phase. So the concentration of particles depended on the added of salt amount. And here are shown the captured image of the formed strontium sulfide particles, which are surrounded by a series of diffraction rings in millikub water and the entire video frame. And this diffraction frame is mainly caused because when the light waves scatter and the particle, then we can see become visible because light waves bend behind the particle, and these diffraction frames are also shown visually, and it helps to detect the nanosite that the particle really exists. So it improves that this system works. And here are shown the size distribution of the average concentration of particles from the entire measurements in the closed equilibrium system. And as you can see, at the lower concentration of salt, in this case calcium sulfide, only small nanoparticles were presented in system. Here in x-axis is shown the size of particle in nanometers, and in y-axis are shown the concentration of particles per milliliter of solution. And when we added more salt, then you can see that all different particles from different sizes appeared in the system, and bigger particles were more visible, and because and also we can detect by visually them if their sizes are over 450 nanometers, then they are seen by visually already. And also the concentration of particles in the system rise all the time, so different sizes, and this can be detected by nanosite system. And here are the same experiment and size distribution in case of strontium sulfide in water solution. And here are seen also that when we add more salt into the system, then more particles appear in different sizes. And if you add then more than this previously determined 1.67 here are shown in this graphic, that they are visually seen as already in naked eye, but in this case only nanosite can detect, they are not seen visually. And so we can use nanosite for detecting nanoparticles and and we also can calculate the solubility product for nanoparticle in this aqueous systems. And the conclusion of current thesis were the following. We investigated the dissolution process and aqueous solubility of calcium sulfide or strontium sulfide in purified water. And we determined the essential parameters, e.g. pH and solubility product of calcium sulfide water or strontium sulfide water closed equilibrium system by using experimentally measured concentrations of formed ions. Through the modeling, we described their interactions in the structural scheme based on the proton transfer principles and validated them experimentally. So we can use them for further measurements. And we use potentiometric measurement to obtain the pH values, and the concentration of sulfide species were measured spectrophotometrically and by odometric titration. And the solubility of calcium sulfide was evaluated to be 1.733 millimolar. and the corresponding value for strontium sulfide was 1.671 millimolar at 25 degrees by normal pressure, and the pH was 11.22. And the average bonding rate of the hydrogen sulfide gas by 0.5 molar sodium hydroxide solution in the closed oxygen-free test system was experimentally measured, and obtained the transformation speed value was 0.827 micrograms per hour per square centimeter area. So thank you for your attention, for your good questions.
Thank you. Before we proceed to the next most important phase of this defense, I forgot to announce that the supervisors of the team are Dr. Ivan Sekker, Dr. Ergo Rickman, and Professor Thomas Tenno, who passed some years ago, was beginning probably.
Yes.
Now we proceed to the next phase, and welcome again, Professor Marina Valentukeviciene from Vilnius, and you, if you like, you would present your activities or current studies very briefly, and then you can proceed to the questions and remarks and the normal discussion, please. Floor is yours.
Good morning, dear colleagues. Nice to meet you, even online. Well, and I express my gratitude that you sent me this interesting dissertation. It's really well prepared. What I'm going to say that 8 articles in international journals and conferences, really big amount of research published. So let me begin from advantages of this dissertation. I like state of the art because there are nearly 100 references, which is important. 97, let's say, if they are all references related to your research, it's really clear and easy to read and easy to understand. First introduction section is really logical. Well, I'm agree with that. Maybe I'm thinking about methodology, but we can discuss it, of course, that you're using measurements with spectrophotometry, which is easy, simple method, but we can discuss what we can measure without spectrophotometry, if you wish so. Also, there are few very insignificant mistakes or inexactitudes in your subsection of conclusions, because everything okay, everything clear and clean with your writings about results and part of discussion about results, but when suddenly into subsection of conclusions, you're writing as seen from the experimental results, the solubility of strontium,
Kas su enda varvas ei olla või?
Could you give some explanation on that? That was the question, I understand, right?
Yes, maybe it is some explanation about it, about your conclusions. What do you think about those experimental results? Because temperature was constant. And you're writing that this is dependent on pH. So maybe you can give some short explanation.
Could you explain that, please? Mr. Candidate.
Yes.
Uiga?
Yes.
Could you answer?
Yeah, the first, how many samples you want to ask? Yeah. At least 3 replicates were made at each concentration, and the mean value was registered. And the number of samples for validation depended on specific experiment and research design. Typically, a sufficient number of samples are used to establish statistical significance. Replicating experiments is generally possible if similar equipment and procedures are available, but depends on the complexity and the resources required for the experiments. So it's the short answer for that question.
Yes, thank you very much for your explanation. Of course, you did right with statistical evaluation for your experimental model. And the next question, or question number 2, if there are changeable variables, for example, pH, different concentrations, etc., how you do with this model, we deal with uncertainties. We cannot be certain, for example, for exactly the same concentrations all the time. So
yes, the change. Okay, I answered the question. Changeable variables like pH and the concentration of ions can introduce uncertainties, and researchers often conduct sensitivity analysis to assess how variations in these variables impact the model's predictions. So in our case, we try to minimize the other factors that may influence, for example, oxygen, that may influence the system. And when the oxygen goes into our system, then it doesn't got the right results what we expect. So we purged the system with inert gas to avoid this situation. And we made 3 replicates at least at each concentration which were measured in this case. Yeah, it's understandable.
yes, yes. Well, thank you very much for explanation for second question. And let's move to the question number 3. It's very complicated when you are working at wastewater treatment plants because we are getting different flows with related pollutants for this model. Is it predictable or non-predictable? Because calcium is extremely reactive metal, and strontium is a principal hazard. In case of strontium is getting into the wastewater treatment plants, it will be disastrous. So
Yeah.
Can you explain a little bit? Maybe we can discuss a little bit. Is it predictable or non-predictable?
Yeah, because the predicting wastewater treatment plant performance can be challenging due to varying influent conditions, but models can be developed to provide predictions based on historical data and operating conditions. And predictive models of factors like impurities and non-equilibrium condition can affect the parameters of the system. And we can use this modeling to predict what will go wrong if some parameters change occasionally or suddenly, what we doesn't expect to be happened. So this model helps to avoid these situations in real systems, in natural waters. And the strontium ion is also more toxic and may cause health problems for humans also.
Yes, thank you very much. Well, it's more or less predictable.
Yes, in this case.
I got this idea. Let's discuss experimental measurement of the closed equilibrium systems. Of course, it is scientifically proved, but what about real situation in shale oil systems? Actually, in Lithuania, we are not quite advanced in shale oil systems. So can you explain a little bit?
Okay. Other models or methods for removing hides from wastewater may be related to dissertation if they involve similar chemical processes and the relevance depends of the specific research focus. The solubility of calcium sulfide or strontium sulfide in water is a topic of interest in this dissertation, but it may not be the main decision. It depends on other research objectives also, and we can use in our model, for example, our problem is mainly caused by the oil shale industry, but also the wastewater treatment plants may be the same issue. If like long pipes, then the anaerobic conditions occur and the toxic dihydrogen sulfide forms, which is very dangerous for living species and organisms.
Yes, and thank you very much. And let's move forward. Question number 5. Of course, there are significant advantages and some small disadvantages of predicted systems. And can you explain few main differences between predicted systems?
Predictive systems offer advantages like cost savings and efficiency, but may also have some disadvantages, such as limited accuracy and the reliance on assumptions. So when we predict, we can not know what all the parameters maybe influence our system. When the one parameter changes, then the cost change of the whole system. So we further like to investigate more complex systems is possible, because there are many different ions in natural systems. So the system is far more complicated in these cases.
Yes, I'm absolutely agree with you. It's really complicated.
Yeah.
We used to try also a few systems. Sometimes it is okay, but sometimes it just doesn't work. But of course, let's move forward. Question number 6 about solubility of your investigated compounds in water. Well, it is well-known phenomena and some novelties, of course, related to nanoparticles and nanomaterials. Is it the main decision of this dissertation that you are related with nanoparticles and nanomaterials?
No, it was just because we had this nanoparticle tracking system, and we find out that it's very cost-effective and easy to use, and we can track also the smaller particles which are not visible by naked eye. So the reliability of nanomaterials in practical applications depended on various factors, including material properties, stability, and the specific treatment process. And theoretical background for the solution mechanisms should ideally correlate with experimental measurements. If they don't, it may indicate limitations in the theoretical framework in the real system when we compare our model and real life. So it may be a little bit different. And also nanomaterials are quite new science field, so it's a lot to investigate in this area.
Yes, your answer is absolutely right. Actually, when we are talking about nanomaterials and nanoparticles, they are a lot for the future investigators. And let's discuss a little bit more about nanoparticles. My question number 7 about properties, importance, and application of nanoparticles. But also, nanomaterials can be related to some possible treatment processes. Are they reliable for practical appliance? Like, I'm going to the wastewater treatment plant and saying, okay, we can use some nanoparticles, some nanomaterials. But they will ask me, is it reliable for practical appliance? Or maybe just scientific investigation? What do you
Yes, these methods are practically applicable because statistical difference was below 5% between theoretically predicted model and our experimental results. And the choice of materials and methods for sample analysis is likely based on their suitability for research objectives and available resources which are given. So also we have to make it as simple as possible, because we didn't have more expensive techniques to use right now, but in the future maybe where more possibilities, then we can also give even better results and even more smaller particles to analyze further.
Professor Valentin Kivitiene, do you hear us? Because your video screen is frozen now. Can you hear us?
Yes, I can hear you.
Okay, we can hear you
Okay.
too. Maybe that's a technical failure, but we can continue. Are you satisfied with the last?
Yes, I can hear you perfectly. I don't know what happened with this.
Okay. Will you
So-
continue? We
Yeah,
can't
we
see
can.
your just frozen your picture, but we can continue hopefully.
Okay, we can continue. And the question number 8. Does theoretical background of the dissolution mechanism of your investigated particles has strong correlations or maybe weak correlations with experimental measurements?
Yes.
Yeah.
The answer is yes, because we used standard methods which were applied on the basis of availability of materials, and we also calculated because economical considerations are also limited in our laboratory. And besides, the statistical differences was below 5% between theoretically predicted model and our experimental results. So the standard procedures for solubility and pH determination are chosen based on their suitability and reliability. And in our case, they showed good results and correlated very well with theoretical model.
Yes, I agree with your answer. It is quite strong correlations with experimental measurements. And can we move to the question number 9? Well, I would like to hear your opinion. Why are you using certain materials and methods for analyzing all your samples from deoxygenated solutions?
And the answer to your question is that the close agreement between theoretical calculations and experimental measurements may be due to accuracy of the model and experimental setup. So we used for analyzing these methods that we have previously used for analog cases. And in our laboratory, what was possible, and also the NTA system was quite useful for further experimental design. So that's maybe the answer.
Yes, this is the right answer, and well, I don't understand why my video is not moving, but we can continue without this video anyway. Let's say question number 10 about experimental materials for determination of the investigated salts, solubility, pH, were all non-standard. And why we can change those to newest one, like ICP or maybe spectrum analysis or maybe something else with this fancy instruments and apparatus in your laboratory?
Yes, these new methods are more expensive because Then we also have to validate these new methods in order to get reliable measurement results, and methods based on pH measurements, e.g. potentiometry, are quite simple and cost effective. Also, using ion selective methods are more complicated to apply because they require addition of other ions that can influence the results of our equilibrium in our measurements. And other methods for removing the hydrogen sulfide from wastewater may be related to this dissertation if they involve similar chemical processes. The relevance depends on the specific research focus. The newest techniques like ICP and spectrum analysis could be used if they provide advantages and are cost effective. So in further research, maybe this is also possible too. And I'm glad to hear your advice in this field.
Brilliant answer. I am agree with you that if we wish to use such advanced equipment, we need to think about practical side of this investigation. And of course, they are highly expensive. Let's move to the question number 11. The results of theoretical calculations and experimental measurements of your closed equilibrium systems are reasonably close to each other. Why it is so? Usually there are some differences between.
It's because they are both alkaline earth metal sulfide first, and their chemical, also the chemical properties like ion radius are quite similar to each other, and they also belong to the same period in Mendeleev's table. So their chemical properties are very similar also in this case, as the results also showed. Only the magnesium ion was remarkably significantly smaller solubility, and it doesn't because its solubility product value is the smallest among others in this among this alkaline earth metal sulfide ions. So it's maybe the cause.
Yes, there are such reasons, of course. We are close to each other because it is, well, chemically reasonable. Okay, and question number 12. There are some other methods, of course, how we can remove hydrogen sulfide from wastewater. How those are related to your dissertation experimental results?
In our case, the system was closed, but in natural systems, they are mainly opened. And then when in case of open system, the toxic dihydrogen sulfide reacts with atmospheric oxygen. So it forms like calcium sulfide or this calcium sulfide precipitate in the polysulfides also may form. So they are in a case of wastewater plants, then aeration is used, and it also helps to remove this toxic gas from the system if you use aeration with air.
Yes, well, we are doing much the same in Lithuania, so I'm agree with your answer. And one more nasty question about strontium toxicity. Usually it is related to the radioactive dosage on living organisms, but there are some exceptions. Can you explain some of them?
Strontium toxicity exceptions may relate to different chemical forms of strontium or its interaction with other substances. And the strontium also absorbs into human bones and make them fragile or cause even cancer in case of radioactive strontium ions. And further details would be needed for precise explanations. In this case, in Estonia, there are also in the north part of Estonia, there are problems with radionuclides, and because they are in this dictonema part of the oil shale. So there maybe also be a health problem for humans who live there and cause some many issues for their health.
Yes, there are a lot of them related to strontium toxicity. You're absolutely right. And I'm moving to the next question. Of course, some results in your dissertation are contradiction to other research work. For example, when you are writing something about detection and dissolution of soluble particles, it is really depending on the size distribution, but can you explain a little bit why?
This contradiction is mostly related to different analytical methods which are used, because the nanoparticle tracking analysis system can detect smaller nanoparticles in size over 10 nanometers. But visually, we can estimate only the presence of larger particles in size over 450 nanometers when the light scatters from these larger particles. Also, the accidental entrance of oxygen or other reactive gases can influence the results of measurements, and contradictions with other research works may arise from differences in experimental conditions, methodologies, or interpretations of data. So that's maybe the answer to your question.
Yes, this is the perfect answer. Thank you very much. And now, question number 15. If you will remember figure number 10 from your dissertation. I hope you remember this figure.
Yes, this image, yeah.
Yeah, you catch the image of particles surrounded by diffraction rings and etc., but it's not explained. You explain a little bit when you present your dissertation today. But well, for most of persons who are not very professionally related to your topic, it's really something like, you know, blurry view, like black hole or something. So can you explain a little bit how you catch it and why it is important for your dissertation?
As seen in my presentation, the encaptured NTA software image diffraction rings are visible around the particles which are formed in aqueous system. And besides, the larger particles are more visible with bigger diffraction rings, because light waves bend behind particles present in the aqueous strontium sulfide or calcium sulfide solution. And figure 10 likely shows an image of the strontium sulfide particle as one particle that is formed in water environment, possibly captured using this NTA system. And more context from the dissertation would be needed for detailed explanation, because it's the actual video frame which the program registered, and we took this registered video frame, for example, to show that this particle really exists, and there may be even more particles if we add more salt. So it depends also the salt concentration.
So you catch the particle and you show to existence of these particles in your dissertation. This is really good. Let's move to the question number 16. Can you explain the meaning of your statement in your dissertation? It is written, the first detectable particles in the analyzed samples were measured. Why the only first detectable particles?
Yes, the smallest nanoparticles in size of 10 nanometers or over, that size can be detected by the nanoparticle tracking analysis system. And the first detectable particles likely refers to the initial appearance of these particles in the samples during the experiment, which are visible. And you can see that they are quite small, but the system can register them even if we don't find them in this frame, but the system register if the particle size is over 10 nanometers.
Yes, I'm agree with your answer. Well, and there are 2 questions left. So one question is about experimental modeling. What do you recommend, for example, for Lithuanian scientists or for Baltic region? Can we use your experimental modeling? Is it?
Yes, we can use.
Countries?
Because the modeling can be used for predicting and controlling dihydrogen sulfide emissions or in oil shale ash landfills, in sewage sludges, and combined by composting when the anaerobic conditions occurred, and also dihydrogen sulfide forms. So we have to give enough air rate, in some case more, to avoid the formation of this toxic gas. That's maybe the answer.
Yes, that's important. You can recommend it to other scientists and other countries, maybe both regions with the similar issue. And finally, well, few recommendations for the future research, or maybe main engineering issues. If you are the engineer, what can you recommend for the future?
Well, for the future, for example, our model can be used for modeling oil shale residue monitoring and the sewage wastewater treatment plants, processes control and monitoring in general. And the future research directions and the engineering issues would depend on the dissertation focus. It could involve exploring related phenomena and or addressing practical challenges. So it's maybe even more practical use than we currently know. So the future studies may apply more that our model works in natural environment also.
Yes, it's very important for the natural environment, of course. And the last question is about, is it easy, simple to repeat all those experiments and modeling from your dissertation if, for example, in my laboratory, they are absolutely similar equipment?
Yes, because standard laboratory equipment was used and the experiments were performed according to standard methods. So these methods are already controlled and improved their reliability. So that's maybe the answer. That if we use new method, then we have to validate it again, and it takes time in some case.
Yeah, yes, absolutely. It's very, very long experimental procedure, but well, thank you very much for your opinion. And I would like to say that doctoral student, of course, can be awarded by degree of doctor in environmental technology. He answered all the questions. I'm really, really happy with answers. So thank you very much. And I'm sorry that it's something happened with the video, but I can see myself on my computer. I'm moving. So sorry for that.
Yeah, thank you very much. We still can't see you, only the fixed figure, the frozen one, but we could hear perfectly, and we can continue. The technician is not here, maybe you're on the way, but now we proceed to the next phase of the defense. Please, committee members, if you have some questions or remarks, recommendations, please. Yeah, Dr. Peter.
So you are looking for a good questions. I think my expertise is the farthest away from this field, so I'm sorry if my question will be naive, or so I'm not trying to trick you, I'm just trying to understand. So first, I was very happy with the thesis, how it was written. I think it was the thesis with the least typos and the kind of issues in the recent years I have seen in the school. So that was very good. It was very readable. I'm curious. So you started the PhD quite some time ago.
Yes.
So I wonder if the aim of the thesis or what you were like doing, did it change a lot from the initial plan? I would say, like what you end up with, does this thesis, did it vary a lot from what was expected from you when you were presented with the initial PhD plan?
Yes, that's right, because when I first came to study this theme, then the model was quite simple, but then when the time about the 10-year period, then our model, what was first model, it implemented all the time, and we also find resources for applying new techniques like NTA measurement in addition to give more precise results. And so it's now more accurate, and we can apply it in many fields in the future, I guess.
Then on page 13, you are writing that you were doing these experiments at a temperature of 25 degrees. I just wonder, like, does it do the results change a lot with the temperature? Like, if I would say if I do it on 20 or 30 degrees, would I get like different results? And if you like read the literature and they do it on other temperatures, can you really compare, or is it like 25 degrees that everyone is running it?
Yes, because the temperature must be constant, because the solubility or dissociation constant of water, KV, known this parameter, it's also temperature dependent. And when we use other temperature, then it changes also the pH. In case of like when there is also water with no other ions, also the temperature influences this pH measurement result. It's also we also have made experiments and showed that the difference exists. But 25 degrees is most widely used temperature, so we can better compare the other researchers' work who are taking the same range at room temperature 20 or to 25 degrees. It depends on this whole what equipment was used and so on.
And I wonder, you were on page 25, you write that you are using this closed system, right? So there's no oxygen, and I'm like kind of wonder that what you are trying to do, if I understood correctly, you are trying to model something or to catch the processes that are happening in the nature, right?
Yes.
So in the nature, there is no oxygen, or I'm just wondering, like, if you do this as a closed system, is it like applicable in real world conditions as well? Like,
okay. In our case, we only studied the closed system water phase. We omitted the gas phase because when we add the gas phase, then this system becomes more complicated. We have to also the partial pressure of gas we have to take into account, and also other gases what may present and affect
mingi
the
üle 10
result.
aasta midagi jama olnud, noh. Mis vastab vist küsimustele praegu. Ja, ma mõtlesin, ma teen samal ajal kahte asja vaatan. Ja.
Sulgege mikrofonid.
Aga töötab kindlasti juba ammu ja siis nagu täpselt töö kõrvalt.
Ja, ma lihtsalt pusin niimoodi kogu aeg.
Ei segaks.
Mikrofonid sulgedega, jah.
Mingi Leedu ülikoolist keegi.
Sulgege mikrofonid, kes kell lahti hoian.
Palun pange oma mikrofonid kinni, te segate praegu kaitsmist. Aitäh.
Jõudis kohale.
Okay, so little technical status. Jan, you like to ask more?
Yeah, so these methods that what you do now, that still can't be applied in this sewage water treatment as it is. Is that correct?
Yes, because we also made some experiments in our pilot when we pilot the wastewater treatment system. Ivar's field right now. And also it was the main issue to get controlled, for example, the pH level in this more complicated systems in natural or wastewater treatment plants. So for this case, for example, the hydrogen sulfide may make living organisms where we can't. This water is hazardous to environment if we just leave it like that is, and we doesn't make further purifications or to remove these toxic gases. So we can't let it to the natural environment. It may cause big problems. First, we had to neutralize its water in some cases before we can let it out from treatment plant.
Thank you. Thanks. Any other questions, please? From committee members? Yeah. Oh,
To me, it seems that you make publications into ranges, something with the goal 5-10 year difference. Beginning of in the range 11. 2011 is the one, and you made lots of modeling studies on that page, but then you have one of the last page, 2020, you have a publication about nanoparticles, and in the nanoparticle papers you don't do too much modeling, you don't do too much measurement of nanoparticle measurement, and the concentration range where you observe the nanoparticle presence are below 1 millimolar.
Yes.
Already, but most of the experiments done with the measurement of solubility were above 1 millimolar range.
Yeah.
Could nanoparticles influence that sort of you found out later that nanoparticles existed in your system? Is my interpretation right?
Yes, that's right. Because nanoparticle tracking system enables to detect very small amounts of these existing particles. Yeah, if yeah. Yes, and this detection area remains between 10 to 4,000 milligram per liter concentration. Yeah.
When you published the first papers, you didn't consider that you don't have two solutions. You have nanoparticles present in your experiments.
Yes, that's also because we didn't have at that time technique to observe them and detect. And later, when we got this nanoparticle tracking,
Now, those experiments, are they, could they be evaluated some other way if you know that there are nanoparticles present in the solution?
yes, also because it gives us more precise results when we use the newer techniques to detect. And if, for example, like opponent said, if there might maybe also some radioactive parts and they are maybe caused big health problems in very low concentrations. So it's important also to detect them earlier than they are visually seen in solution, for example. And these new methods gives us this opportunity to do that and to warn, for example, if something goes wrong, then the humans know that this water is not drinkable or so. Yeah.
In the you start with this that relates to the oil field industry and chemicals and that what and based on your modeling, how can it be used in your modeling? So you just refer your own saying that modeling can be used for predicting the regulation of the. After your modeling, what can we do better by managing management and predicting the skill and chemical problems? Can you maybe very popular way say what the modeling can do?
No, our model, for example, inside the oil shale residue, this pile, then the anaerobic conditions may also present inside this like pile, so it may cause high pH leachate when it reacts with water, and this leachate is without neutralizing, it's very dangerous to let it out into the natural environment. pH may be over 12, so this water is highly alkaline and may cause many problems.
Sorry, I think opponent is not hearing us when the questions are given. Can you hear me now?
Yes, I can hear.
Okay,
you.
I give the microphone to the committee members if they are asking.
Oh,
Sorry.
Yeah, okay.
Okay, I will not repeat those questions anymore, but the strontium concentration, for example, are they in the range what you were studying with your modeling, with your experiments in the leachate?
In case of, for example, oil shale residue, the concentration of strontium is around 1,000 milligrams per kilogram of oil shale, but residue. But in case of calcium sulfide, it's even higher. It may be 20 or 40 grams per kilogram. So it's calcium sulfide is the main problem in our case, and also the other sulfide forms what may be in this residue.
Okay, any more questions? Yes. Give him mic, please.
Thank you, Kadri and Tam from Tallinn University Technology. First of all, I totally agree with the other colleagues that theses were written very nice academic English, and it was easy read and follow. So thank you, Kalev. Okay, but my main question actually, we have these two heroes. We can say heroes, yes, calcium sulfide and strontium sulfide. Okay, of course, we have the HO2 water, as you mentioned, but what is your opinion? Which of them gave for your this equilibrium model more effect or effort to build up this model? Did you understand my question?
Yeah, I can generally understand. In when we think about Estonia, like then the main problem is probably calcium sulfide, and then we also think that it will be useful to investigate other magnesium sulfide, barium sulfide, and strontium sulfide from this alkaline earth metals because they belong to the same period in Mendeleev's table. So we tried to make this investigation more large than it was at the beginning.
Okay, if I understood correctly, that anyway you started with the calcium sulfide and you tried to build up the same model with the strontium sulfide, and due to they activate in the same way, you then try to use the magnesium, but then it doesn't work.
Yeah, it was because also the solubility data confirms that the solubility of magnesium and its compounds are very slow. You know, in case of, for example, magnesium hydroxide. Because its ionic radius is the smallest. And also the literature data in some cases are big variation when we also try to find out, for example, the solubility product of calcium sulfide or strontium sulfide, then we got the numbers which were different over 10 times. So the difference is also maybe caused by different methods which were previously used, and they gave probably different results in common.
Okay, I have maybe like strange comment or thought that we have this equilibrium constants, and if we took like the second acid dissociation constant of H2S, what you showed also, and I was a little bit like confused. There is like sometimes it's like equal. If you look these equations, there's something like equal, and sometimes it's like approximately equal. Why is what like a mistake, or did you like really thought that you should mark it like that? It's a page 19. Yes.
Mm-hmm.
If you look the equation 6. And after that, below that, it's equal, but in equation it's approximately equal.
Yeah, the KH2 values, as I said, differ almost 7 orders of magnitude. So we also had the main issue to take for our modeling, which number, because the difference was so big. So we have to do this work by ourselves to determine which goes best, which shows best results with in case of our system and our modeling. So we compared the different KH2 values to each other and our experimental results, and took the closest what's correlated with our real experimental results. And then this was the number which are shown in as 1.2 in the power minus 15 was the closest correlation what we found out.
Okay, thank you. Okay, the last question, because I already got answers before, but let's back to the experimental part. I'm still confused. How you why did you use those times to do these experiments, like 3 days and 10 days, to have this equilibrium state? Maybe can you describe it more? Why, how or why or when you decide to use those experimental time when you ended your experiments? Like it was like 3 up to 10 days.
Yes.
Yes.
It was related to the added salt amount. If we added more salt, then it also takes a longer time to go this salt when it dissolves into water, then it goes slowly to air phase. It takes time to reach the level enough to absorb from alkaline solution. So in larger amounts of salt, it took also longer time to get the right results. When we first take too little salt, then already few days there's equilibrium was established between the liquid and the gas phase, and no further time was needed for this experiment. But if we took more salt, then it takes also lots of more time in order to establish and to bind this hydrogen sulfide by alkaline solution. It takes a longer time.
Okay, thank you. That's all.
Thank you. Any other questions, please? Yes, I was expecting, not going down.
Okay, nice presentation and nice work. And actually, well, I'm from the, let's say, the applied for practical side, because I've been working with oil shale ashes, residues, and semi-coke for about 20 years. And this calcium sulfide, it's actually a solid phase. The mineral called oldhamite has been a real trouble to us in different ways. And therefore, actually, its solubility, dissolution, and the hydrogen sulfide emissions, those are all related. But actually, the question that I'm asking, actually, what I had, the question that actually was already asked, this is about 25 degrees, because in real life, in nature, actually, you have freezing temperatures of close to zero during the winter, and then you have plus 30. So it's like the huge variability there. But you answered that. But my question is more out of curiosity, because your paper about the calcium sulfide solubility came out in 2011, was it? Yes.
First paper.
A year before the last person asked the question you published her paper. And I'm asking, okay, your solubility was about 1.7 millimole, or something like this. But her experiment was 2 point something. Why so different? Okay, not that different, but still why different in inert environment?
Okay. I guess the difference may be because in our case we used closed system. But
well, they used closed system as well.
Maybe in their system there were also other ions except calcium sulfide. Maybe more, or it was only the same. And or the oxidation was maybe the topic. In some case, the oxygen we removed as much as we could by purging with nitrogen or argon before the experiment, because when it leaves in this oxygen in the system, then it gives different results because calcium sulfide precipitate already forms, and it may influence the whole system.
Okay, well, this actually shows how difficult are those systems to study experimentally. Okay, thank you.
Yes.
Yes, and I have my chance to ask also something that was already touched by several comments. I was a little bit confused. I was thinking in the beginning, you are talking about the wastewater coming from the industrial part, okay? The oil shale and also the semi-coke. And in your answers and also in the discussion, there was a lot about sewage, which is different story. I think it's not, do you think your model developed for the equilibrium closed system is suitable to describe everything what is open, especially the oxygen problem and the precipitation of calcium sulfide and strontium sulfide? By the way, strontium is more dangerous than calcium.
No, in our results, it may be if we took, for example, these sewage pipes, which may be quite long, then when it's over 1 kilometer long, then at some point the anaerobic conditions may occur in the end of this pipe.
This is a theoretical assumption. You didn't do that in your experiments.
That's. But in real life, it may be caused problems when this effluent, what's at the end of pipe goes into the environment without purification. Then it may cause that organisms die, living organisms, if this toxic dihydrogen sulfide immediately goes into natural waters.
But the origin of the wastewater is quite different. I mean, municipal wastewater, which is mixed industrial and sewage, and the really sewage, human waste or animal waste. This is a different story. A lot of organic compounds, and then the treatment is really different. But anyway, if you think it's you might try this model for these systems.
Yes, I guess it may also one option to use in different cases if this problem arises. For example, in Kohtla-Järve, it was this problem that was described, but there are mainly industrial wastewaters which are causing problems.
With H2S, that was a big scandal, of course. But anyway, more question? Uno?
Thank you. At the end of your thesis, you are suggesting that the further investigation is needed to describe the calcium sulfate and strontium sulfate solubility in water and develop new models. But what will be your next steps to continue this work?
The next steps may be, if we continue, then to analyze also barium sulfide further, because we did only initial experiments and maybe more sulfide species that may cause problems, for example, in Estonia, because there are a mix of different ions when we took this residue, and they are also influencing each other at some point in the real system. So we have to make this system more precise, and it may be more complex in real environment than in our model when we took only one substance. But in real nature, there are more than one substance actually, which may influence the whole equilibrium system.
And one final question from me is that also related to oil shale industry, because you're talking about it in the introduction and also in summary, and I was wondering that how and if you could use your current results for to work with this kind of hazardous materials, and how can you describe it? Like, what is how can your thesis results be used for that purpose?
No, for example, when we use like nanomaterials, then this topic maybe also maybe cause because nanoparticles maybe also cause health problems if they come to, for example, the human organism, and we have to detect them before it happens. So, for example, the NTA systems enables us to detect this even the radioactive nanoparticles that may present in waters. So it's maybe good to inform our humans before we take further steps.
Thank you.
Thank you. More questions from the committee members? No recommendations, no remarks. Then please, the whole audience is allowed to give questions. Marko, you.
My question is, can you explain in short and well understood terms how your thesis is defended in environmental technology, not in chemistry?
This team is actually what our previous supervisor and Thomas Tenno think that this topic is very important for this, and then it was also actual discussion team, and that's the reason why we took. I was also my bachelor thesis was environmental team, but I changed the team, and there was also like a discussion about where to defend environmental or chemistry, but chemistries are more, I guess, they ask questions more about this model, specific things. Maybe that's the point, but the environmental problems may also be important in our case more than this discussion about which more reacts or doesn't react. So it's maybe the great answer.
Thank you. This was a good answer.
Well, for our opponent, it's just the never-ending question about where it should be defended, because the environmental technology is really very multidisciplinary, from remote sensing, satellite analysis, up to the mycorrhiza studies in really, or molecular level studies over chemistry, over other physical questions. So I think, yeah, it's a good answer what you gave. I also agree. Thank you. And yeah, Professor Peter Burk.
Thank you. Nice work overall, but I can compliment your answer with short saying that such kind of thesis would not be defendable in chemistry. With that kind of using of words, terms, notations. The idea itself is okay. I think if you just rewrite it a bit, it would be defendable there also. But as is, it's definitely not defendable, because there are very many things what chemists just say different.
Yes, different
so
views.
Bonding of gaseous H2S, what does that mean? To what it does form a bond? The chemist would ask you immediately. But that's just a comment. But let's go to the questions. There is one question which I usually ask our bioorganic chemistry people when they present similar to yours equilibrium constants. In physical chemistry, which I apparently teach for the first year students, I say that you can use concentrations, of course, but keep in mind that in reality, the equilibrium constant relates to, and my question is what?
Equilibrium constant temperature, for example.
No. We have given can you, if you want to be really precise, can you use concentrations in your equilibrium constant expression?
Solubility product maybe in some case give more exact result.
No.
But
what would be needed for exact, correct, in physical chemistry, correct way in those in those equilibrium constant expressions? Because why I dare to ask that, you at the next page or on the page 16 mentioned something related to that.
It depends also used method, or it's just.
Let's say that we know precisely what the concentrations are of all species in our system.
Yes.
Can we use those concentrations to get the correct equilibrium constant?
If we avoid or only used measurements in water phase, but minimize the gas phase volume, then
if you have a simple case, just dissolution of something which does not give you a gas phase product, even after the hydrolysis, can we then use the concentrations?
No, then, for example, when we took salt, like
I will answer for you. No.
Yeah.
In physical chemistry, equilibrium constants are defined through activities. And activities might be very close to the concentration, but especially when you have higher concentrations of different ions, then you should take into account also activity coefficient, which is mentioned on the page 16. And then there might be difference. So perhaps some of your problems with different measured equilibrium constants also stem from the fact that you just use different concentrations, meaning that the activities are a bit shifted. But that was just...
Yes, I know that it may be issue.
Just the start. Yes. Just the start. I have decided to interrogate you a bit more. So you on the bottom of the page 15, you write that you have written the chemical equilibrium for the hydrolysis of sulfate ion, and write that this very simplified approach, equation 4, is not entirely correct, as it assumes a reaction between sulfide ion and water molecule. Actually, the decisive factor in the formation of chemical equilibrium is extremely rapid dissociation of water. How can you differentiate? Which is important? Either the reaction with water or reaction with proton?
Well, it's because the proton transfer model which we used, then water, when it gives 1 liter water about 55 millimoles, then it's maybe the proton centric. So if water gives protons, and these additional protons are binded by sulfide ions, and so that's why the pH also increases, because hydroxide ions become dominant in this aqueous solution, which contains transfer or calcium sulfide. So
what would be the difference? The proton jumps directly from water molecule to the sulfide. Then you also produce OH anions.
No, because OH ions become dominant. Protons are binded by sulfate ion. So they are binded together, but the excessive amount of hydroxide ions, they are presented in this aqueous solution, and this causes the increase in the pH values as shown in this graphs shown in this presentation.
All right. Yeah, I think you have to use deuterium, the labeled hydrogen, or protons. That might help. But anyway, this is more expensive and much more expensive than your methods you used.
Yeah, we use the simplest method.
The proton transfer mass spec and all the isotopic values. But maybe it's a future for you.
Yes, it's used in further studies. I think that cooperation with chemists are very useful. If we take larger systems to investigate, then
absolutely, and we should keep some common wording when communicating with really engineers building up the systems. Not talking about activity of the, but concentrations. But anyway, more comments, questions? I don't see. Thank you very much. And as our common procedure foresees, you might have some words at the end. Okay. Before I send all the audience out except the committee members.
Okay, thank you all for coming, especially the committee, and the questions were very interesting and useful for further studies. And I take all the suggestions into account, which were made by committee members. And also I want to thank my supervisors who helped me to finish my work, Ivar Secker and Ergo Rickman, in the many colleges, and co-authors that were also in our study and made cooperation. And also my friends and family, thank you for your support, and I hope that it helps me to find more ideas in the future for further investigations in this field.
Thank you very much. And now, please, audience, you are pleased to go out, and we will inform you about maybe 5 minutes or how long time it takes discussion between the committee members. And can you hear us good, dear opponents?